Welcome everyone, my name is Thomas Greenlaw and this is our group project presentation for the search for intermediate mass black holes. First, just a bit of an introduction. So an intermediate mass black hole is one with a mass that sits between 100 solar masses and 100,000 solar masses. They are larger than the stellar mass black holes created by supernova and smaller than supermassive black holes we see in the center of galaxies. There's a very active field of research for looking for these black holes at the moment, because we can't seem to find a lot of evidence that they exist. And it was only very recently that we observed our first intermediate mass black hole. We're also not entirely sure why this is the case. In this report, we'd like to shed some light on the issue. We're going to talk about how intermediate mass black holes can possibly form, and that's either through direct seeding or through evolving and accreting mass into the range. We will then evaluate the potential candidates and the techniques used to observe them. We will then briefly introduce the physics of gravitational waves and how they can be exploited to measure intermediate mass black holes, specifically binary black hole mergers. And then finally, we will discuss where the future of the field takes us. First, I'm going to hand you over to Hugh, who's going to talk about seeding mechanisms in the early universe.
Hello, I'm Hugh Beaumont. The seeding mechanisms by which IMBHs are formed play a vital role in the peculiar rarity of this class of black hole. If one were to imagine that the number of ways in which a black hole could be seeded in the IMBH mass range has shrunk over time, then it would immediately follow that the population of IMBHs would deplete as instances of the species evolve into SMBHs. How might it be that these seeding mechanisms could be unrealizable in the modern universe? There are three seeding mechanisms which have been identified by the literature by which IMBHs are seeded. By understanding the conditions by which these channels occur, one will discover that only one of these is accessible in the present universe. The three channels are the direct collapse of a large gas cloud, the supernova of what is referred to as a population 3 star, and the gravitational runaway of a stellar cluster. Addressing the direct collapse channel first, this process comprises of a large unstable cloud of pristine gas collapsing upon itself. Pristine gas is gas which is characterized by a very low, indeed approximately naught metal content. If certain conditions of the cloud are met, then the gas will collapse into regions dense enough where a quasi-star is formed, which passes through all the stages of stellar evolution rapidly and collapses to within the Schwarzschild radius to form a black hole. These black hole seeds can be as large as 1 million solar masses, right at the upper end of the IMBH mass range. The principle of the aforementioned conditions are that if they are not met, then the gas cloud will simply fracture as it collapses, and the gas will not be dense enough for a black hole seed. If the angular momentum of the gas cloud is too high, then due to asymmetries of the cloud structure, fractions of the gas cloud may be ejected as the cloud collapses. This is illustrated by the two figures on the slide. Each figure shows 4 snapshots of characteristic moments in 2 simulations of the collapsing process taken from a 1994 paper. Each snapshot shows 2 types of matter distributions. On the left are highly dense pockets of gas, where one might expect black hole seeds, and on the right is the remaining gas. In the figure with angular momentum, it is clear to see the gas fragmenting, whilst in this particular simulation the 2 large fragments eventually recombine. A not insignificant amount of gas is lost. In the figure depicting no angular momentum, however, significant fragmentation is avoided. Similarly, if the metallicity of the gas cloud is too high, or the gas cools to a point where H2 molecules begin to form, then fracturing will occur, preventing black hole seeds. Cooling can be prevented by the presence of a high background radiation or the existence of a local radiation source, such as a star. The simulations from a 2014 paper shown in the figure below show the density of H2 gas decreasing rapidly under Lymer-Werner or ultraviolet radiation. This process can be diminished if the gas cloud is optically dense and hydrogen associates into H2 within this region, which is called self-shielding. It is not immediately obvious from these conditions why this channel might not be in principle accessible in the present age. After all, the background LW radiation is much higher than in the early universe. However, after billions of years of stellar activity, the universe has been polluted with metals, rendering the vital pristine gas extinct. Collapsing gas clouds in the modern universe thus fracture too much before IMBHs can form. Direct collapse, therefore, is confined to high redshifts, which correspond to times in the early universe. The conditions for the population 3 stars tell a very similar story. These stars were massive stars of at least 100 solar masses. These stars comprised of almost only pure hydrogen and were formed in the dense, pristine gas clouds of the early universe. These stars could collapse very efficiently without ejecting much material, and the black hole seeds of these stars were in the hundreds of solar masses, which is at the lower end of the IMBH mass range. As previously mentioned, however, pristine gas no longer exists, and so neither do these stars. However, there is some hope in the final seeding channel, which is gravitational runaway. Now, this is the process of a dense stellar cluster undergoing a number of collision events which allow an object to accrete mass rapidly and ultimately collapse into a black hole. Within a few million years, it is possible for a black hole to accumulate enough mass to become an IMBH, and furthermore, with a little luck, the conditions might be such as to prevent the IMBH accumulating too much mass and becoming an SMBH. There is nothing about this channel which prevents it from occurring today. Indeed, in globular clusters, the conditions are ideal for such gravitational runaway events. We will explore these potential candidates later on where modern IMBHs might be found, which were probably seeded via this channel. Due to the relative deficiency of possible ways in which IMBHs may be seeded in the modern universe, it follows that the number of IMBHs is therefore likely to be small. But what happened to the IMBHs that existed in the early universe? The other half of the story, which Tom will discuss next, is the process by which black holes accrete mass and evolve from IMBHs into larger supermassive black holes.
Right, so now I'm going to be talking a little bit about how black holes can increase in mass during their lifetimes. So there are three main processes in which black holes increase in mass. They are tidal disruption events, accretion disks, and black hole mergers. I'll very briefly talk about black hole mergers because they'll be talked about in a lot more depth later. They are quite rare. They can happen maybe only once in a black hole's lifetime, and they are responsible for the single largest increase in a black hole's mass. So far, they're the only thing that has produced an intermediate mass black hole, which was measured a few years ago. GW190251 was a gravitational wave coming from a black hole binary merger, which resulted in a black hole of 150 solar masses. The next process is a tidal disruption event. This is when a star gets too close to a black hole and the tidal forces from the black hole pull the star apart. Some of the mass will be swallowed directly into the black hole, and some of the rest of it will be formed into an accretion disk, as you can see on the top row of the right-hand side diagram. The diagram on the left shows a graph of the accretion due to a tidal disruption event, and you can see that even within a matter of decades, the rate falls back to its pre-tidal disruption event rate. They're quite rare. For most black holes, they occur maybe every 10,000 to 100,000 years. However, there are some scenarios like AGNs or starburst galaxies in which they can occur every 100 years. However, you can see on the diagram on the right-hand side here that mass accreted due to tidal disruption events in some simulations reaches maybe 0.1% of the total black hole mass. So the final way is an accretion disk, and an accretion disk is a disk of gas around the black hole that has a slowly decaying orbit, and once it's reached a certain point, the gas from the accretion disk will fall into the black hole. It is limited by the Eddington accretion limit, shown with the M dot diagram on the left equation on the left-hand side. And here on the right-hand side, we've got a diagram of the black hole mass due to certain fractions of the Eddington accretion limits. It is currently unclear what the overall Eddington accretion ratio is over the lifetime of a black hole. But you can see if it's even below 80%, the growth is going to be significantly stunted. And it shows it's absolutely plausible for a stellar mass black hole to start accreting at even a fraction of the Eddington limit and accrete into the intermediate mass black hole range. This implies that we should be able to find intermediate mass black holes at a range of redshifts, starting seeding at the very early universe, but even closer to Earth as well as stellar mass black holes accrete into mass. I'm now going to hand over to Jamie, who's going to talk about some of the places that we can find such intermediate mass black holes.
Hi, I'm Jamie. Following on from Tom and Hugh, it's now a good point to move beyond background theory and examine exactly how we detect these hypothetical intermediate mass black holes. Specifically, I will focus on perhaps the prime example of an accreting black hole, the active galactic nucleus, AGN for short. AGNs appear as a significant excess of radiation above the usual galactic spectrum, with X-ray and potentially even gamma frequencies that are unexplainable by simpler models. The main theory that these active nuclei are powered by accreting black holes has a wealth of evidence to support it. For example, the extremely high and persistent luminosity, easily over 1 billion times that of our Sun, is most easily obtained through accretion effects, which have a high efficiency of matter to radiation conversion. Furthermore, they are observed to be confined to small central regions of their host galaxies, and as such cannot be built up from smaller, less luminous events. But could they be intermediate mass black holes? Frustratingly, the answer to that is the rather unsatisfactory maybe. Modelling these AGNs certainly allows for the possibility of an intermediate mass black hole core, but the fact remains that despite a number of promising candidates, there are no confirmed intermediate mass cases. There is a strong motivation to search for them here, though. As discussed by Hugh earlier, supermassive black holes potentially form from successive mergers of smaller black holes, culminating in the giants we observe today. AGNs are typically found at high redshifts and could very easily be supermassive black holes at an earlier stage in their existence. A rock-hard discovery of an IMBH AGN would therefore provide strong credence to this model. It could be viewed as the missing link between stellar black holes and supermassive black holes. And finally, the fact holds that the electromagnetic signals from AGNs are simply really good and clear sources of information. It's widely assumed that all galaxies have a central black hole, but accreting AGNs are just much more visible than their inactive counterparts. And as such, there is a lot of potential to advance the field of black hole research by examining them. So how can we measure an AGN black hole mass? Reverberation mapping is one of the most commonly used methods. AGNs are typically surrounded by vast orbiting gas clouds. Radiation from the AGN travels through these clouds, some without effect and some interacting and appearing as emission lines. Typically we have what is known as a broadline region, or BLR, close to the black hole, and a much larger narrow line region further out, illustrated in the diagram on the right. The name broadline refers to the fact that at these closer distances, the extremely high rotational velocities result in relativistic Doppler effects broadening the spectrographic signature. Combining this velocity distribution with the radius of the BLR, we arrive at an almost Keplerian equation, the mass of the black hole, displayed at the bottom here. Delta V, the root mean square velocity of the BLR gas clouds, is measurable by considering the exact broadening of the lines. But R, the radius of the BLR, is more complicated. The key concept is that fluctuations in the accretion disk will also affect the BLR components in the measured spectra. However, this effect is delayed by the finite speed of light, and so there is a measurable time delay between the fluctuations in, say, the luminosity and changes to the BLR components of the spectra. Assuming this delay is solely due to the speed of light, then it is theoretically possible to extrapolate the radius. Clearly, though, this measurement depends on the specific geometry of the BLR, and assumption of perfect spherical symmetry would be a rather naive oversight. Furthermore, the amount and quality of the data required to completely deconvolute delays associated with radiation travelling in different directions before reaching the BLR boundary is prohibitive. Instead, a form factor f is assigned in order to approximate the various possible geometries. This can either be assigned ab initio, basing it on simple simulated models, or it can be assigned so as to fit the so-called M-sigma relation, which empirically relates black hole masses to their velocity distributions, and has been shown to hold for a large number of black holes. This form factor is perhaps the largest issue with reverberation mapping as a technique, due to the varying ways it can be assigned, but this idea of empirically assigning a value strongly suggests that this technique will only be refined over time as more and more AGNs are mapped this way. But reverberation mapping is certainly not the only method of measuring AGN black hole masses, and indeed it is the technique that has little to no application beyond the field of AGN research. If we consider the fact that black holes exist in inactive galactic nuclei and can be located off-center, then it is clear that alternative methods are required. Furthermore, there are cases even for active galactic nuclei where reverberation mapping draws inconclusive results, perhaps due to the especially dense surrounding dust sources or star clusters. And it is the topic of such alternative methods that comes next in this talk, where Finlay will be introducing dynamical methods of measuring black hole masses.
Hi, I'm Finlay, and I'm going to talk about how dynamical methods can be used to try and find IMBHs. So dynamical methods are essentially using the observed kinematics of a system to find the mass of the black hole at the center. So how do we do this? So inside galaxies, we've got a mean free path, which is greater than the age of the universe. So we can use a collisionless Boltzmann equation to find a distribution function, because these stars are not going to collide. So we could use things like the Jeans theorem or Schwarzschild modeling, where we find integrals of motion or assume orbitals and sort of fit them to observations. And these will produce a distribution function, which we can use to find the mass of the black hole at the center. Now, there are problems using these methods. We've got a velocity and mass anisotropy degeneracy. Now, this means essentially we struggle to determine between the inner and outer velocities of stars, and we use the ratio to find the mass of the black hole, so that's a problem. And we also struggle to determine between stellar and black hole mass, which is another issue. We're trying to find the mass of the black hole. We make assumptions of the orbital system, like it being spherical or axisymmetric, or there being a constant mass to light ratio. While they are useful, they may be inaccurate, and means that the mass that we find might not be right. And stellar libraries might be incomplete. And the problem this produces is that we may be missing entire things that can completely change our model. When we're looking for IMBHs, we often look at globular clusters. Now, there are issues with using dynamical methods in globular clusters. The signatures that we look for to try and identify IMBHs can be explained by unrelated processes. So we might look for this shallow surface brightness cusp, but this can be explained by mass segregation or core collapse. It can be difficult to determine kinematic features of objects close to the center of the galaxy. The IMBHs have a very small sphere of influence, and in these globular clusters that are very dense, it means that finding the kinematics close to the center is very, very difficult, as it's dense and small. And for lower mass galaxies, restrictions like irregularity in structure can make it very difficult to determine the kinematics of the center as well, because they're not well defined, and things like bars in galaxies can produce big issues with our models. Also, in globular clusters, we have ongoing star formation and a larger proportion of dust, which can disturb the determination of our mass to light ratio. And individual stars can dominate the light output. Like in this graph, one star produces a lot of lost data, which is the white dots. We also have to take into account that stellar mass black holes could be mistaken for intermediate mass black holes. So we have quite a few issues when we're looking at these globular clusters. We can try and fix an issue by resolving the mass anisotropy degeneracy by looking at the proper motions of stars. The proper motion is looking at the drift of this star in comparison to background positional references. The problem is that because we've got these small IMBHs, even when we use space telescopes, which is what we have to use because the sphere of influence is so small, even if we imagine how technology might progress, we still find relatively small numbers of proper motions for stars, and we don't really fix this mass degeneracy issue. So let's instead look at some of the candidates that we have found using dynamical methods. We've got Omega Centauri, NGC 6388, and G1, which is outside the Milky Way. Now, while we have papers in favour of Omega Centauri, suggesting that it's around 4 to 5 times 10 to the 4 solar masses, we also find papers refuting this mass based on proper motions, and the velocity dispersion they use can be explained by other processes. And this is the same for most other examples, particularly G1, because it's outside the Milky Way. It's difficult to determine it because it's far away and small. So these dynamical methods can find candidates, but it seems like it might be difficult to produce robust evidence for an IMBH, given that there are so many issues inherent with the method. So are there any other methods without these issues that we could use, which could produce a robust example of an IMBH? Well, this leads us to gravitational waves.
Thank you, Finley. My name is Haru, and in the remainder of the presentation, Andrew and I will discuss an alternative source of information for astrophysical systems, gravitational waves. Gravitational waves are ripples in four-dimensional space-time that travel at the speed of light. They're useful in astronomy because not all black hole systems actually produce detectable electromagnetic signals, though they may still detect gravitational waves, which can be used to investigate their properties. Gravitational waves travel as transverse plane waves, which means that space-time is warped perpendicular to the direction that they propagate. This warping results in strains, which are relative changes in length that can be thought of as the amplitude of the wave. They vary with time, are denoted with a h, and are described by this strain equation, which is that change in length is equal to the strain times the original length. The effects of these strains can be imagined for a ring of free particles, as shown for one cycle in this figure. The two rows correspond to the two different polarization forms, H+ and Hx. These strains are in fact tiny, of the order of 10 to the negative 20, which is because gravitational waves actually interact with matter very weakly, which means that they suffer less signal disruption as they travel, but they're also very difficult to detect. Good sources of gravitational waves involve large, rapidly changing gravitational fields stemming from large, rapid changes in energy and mass distribution. Such systems typically involve compact objects, which are bodies with extremely high densities and consequently large gravitational fields, such as neutron stars or black holes. Importantly, characteristics of the wave, such as frequency or amplitude, are strongly source dependent and relate to the dynamics of the source. We can broadly separate sources into two categories, rotating and non-rotating. For a rotating system to emit, it must be asymmetric about its rotating axis. For instance, neutron stars with bumpy surfaces or a binary system. For this dumbbell-like model, you can see that about axis A, there is rotational symmetry and would be no emission, but around axis B, there is no rotational symmetry and hence there could be emission. For non-rotating sources, which we shan't discuss that much, it just can't be spherically or cylindrically symmetric, such as for a supernova explosion that is asymmetric. One particularly interesting type of system are compact binary coalescence systems. They involve two compact objects orbiting a common center of mass. Over millions of years, the orbits shrink due to energy lost as gravitational waves. These waves have frequency twice that of the orbital frequency. This causes the bodies to eventually come into contact and merge or coalesce. By modeling these systems, it is possible to predict the masses of the compact objects involved by comparing gravitational signals to these models. An important quantity in these models is the chirp mass, as described by the equation here. By obtaining the chirp mass of the system, researchers are then able to find good estimates for the individual masses M1 and M2. From the waveform, we can identify three stages of coalescence: the in-spiral, the merger, and the ring-down. The in-spiral stage involves separation gradually decreasing and velocity increasing. This corresponds to a long period of gradually increasing frequency and strain amplitude in the waveform, with a period of rapid increase much closer to the merger. The next stage is the merger itself. This takes place over a fraction of a second and corresponds to the peak in wave frequency and amplitude. During the final ring down stage, the system radiates away additional energy and mass to reach an equilibrium state where emission stops. This corresponds to this point here where the waveform tails off. The evolution of the waveform frequency can be linked to the chirp mass by the equation here, where you see chirp mass, frequency, and rate of change of frequency. For higher mass systems, lower frequency waves with faster inspirals and mergers are expected, hence shorter signals. Lower mass systems emit at higher frequencies with longer signals. Roughly speaking, systems of mass greater than 1,000 solar masses have frequency below 1 Hz, and for lower masses greater than 1 Hz. I'll now hand you over to Andrew, who will discuss how gravitational waves are actually detected in practice.
Hello, thank you, Harry. I'm Andrew. I'm going to be talking about the experimental detection of gravitational waves. For this, we have two main observatories. We've got the Laser Interferometer Gravitational Wave Observatory, or LIGO, and we've got Virgo. LIGO is based in the United States and Virgo is based in Italy, and these work together to confirm their detections. LIGO made its first direct observation in 2015, which was direct detection of a black hole merger with a resultant mass of 62 solar masses. It doesn't qualify it as an IMBH, but it shows that it is possible that we could detect IMBHs this way if they would occur. This did in fact occur in 2019 with GW 190521. Signal is just the gravitational waves and then the year, month, and day of the signal detection. So merger between a 66 and 85 solar mass black hole at 5.3 gigaparsecs. This larger 85 mass black hole lies within a mass gap created by pair instability supernovae between 65 and 135 solar masses, with the 66 having too large an error to inclusively say the same. The resultant of 142 solar masses and the rest being radiated as the gravitational waves we detected. You can see the sigma noise increasing much larger for the Hanford and Livingston LIGO detectors compared to Virgo. This is because they're much more sensitive, and it peaked at about 60 Hertz. The 1 in 4,900 year false alarm rate, which is much higher than the very first detection, which was 1 in 203,000 years. So this shows how much worse we are at detecting these lower frequency intermediate mass black holes. The exact scenario behind it is unclear, partly due to this shorter signal. It is likely a hierarchical merger, which is a merger between second generation or higher black holes, most likely second generation. This could have occurred in a globular cluster, stellar merger scenario, or an AGN disk. It's the first evidence of a high mass binary system. This provides some new insight into this. So how do these detectors work? We'll take a look at the LIGO because it's the most advanced. It's a modified Michelson interferometer. We've got these 4 kilometer long arms with a laser beam set up to destructively interfere, no signal, and then if there's gravitational wave strain, it should constructively interfere and we should detect the signal here. The laser source starts out at 20 watts. It's increased to 700 watts in its power recycling and then split into beams. And with these fabric product cavities in the arms, increases to 100 kilowatts, greatly increasing sensitivity. It's most sensitive between 100 and 300 hertz, the total sensitivity range between 10 and 10 kilohertz. So the 60 hertz of the intermediate mass black hole detection is very close to the bottom and it's outside its most sensitive range. These are limited by noise outside this range. It's also limited by arm length as well, actually. So it's a mixture of intrinsic, such as the Pauli exclusion principle, and environmental noise, such as seismic noise. It's seismically isolated, but this is still very, very high, below 2 hertz. You can see from this brown line on the graph. Gravity gradient, which is just a coupling of the test masses, is also very hard to suppress. You just see it rapidly increasing at low frequencies. Photon shot noise is dominant above 100 hertz. Photon shot is just the randomness of the photon quanta arriving at the mirrors. Though this doesn't really affect our detection of intermediate mass black holes. So these are expected in this lower frequency range. So we need to improve low frequency detections to improve intermediate mass black hole detection. There's some ways we can do this. CAGRA, which is an upcoming detector that's just went online in 2020. It limits seismic noise by being underground, and it limits thermal noise by its cryogenically cooled sapphire mirrors to 20 Kelvin. It's expected to make some significant contributions once the 4th observing run begins with this intermediate black hole being detected in the third run. Then we've got LISA, which is a space-based detector, which should remove most of the non-quantum noise. However, we can't have the Fabry-Perot cavity simply because it's in space, but we do, however, have 2.5 million kilometer long arm lengths, which is much, much longer. Should follow the Earth's orbit around the sun, you can see in the schematic. Expected to be most sensitive, about 3 millihertz, with its target range being below 1 hertz. We should be able to detect intermediate mass black holes quite easily with this compared to ground-based detectors. We should be able to detect anywhere between 600 and 10 to the 4 solar masses. This is a region we have no chance of detecting from the ground with gravitational waves. This is very exciting. So in summary, the future detection of intermediate black holes, we expect them to confirm theories about seeding mechanisms such as direct collapse. LISA is also expected to confirm existence of intermediate mass black holes in the early universe, so it should have a longer range. And these gravitational wave methods, which have provided such a step forward with the first detection, should be used in conjunction with electromagnetic detection to show a clear picture of intermediate black holes' place in cosmology. And we believe that this is very important for the future of cosmology, as it's currently a massive gap. Thank you for listening. I'd just like to say thank you to James Aird for his help and advice on our project. Thank you.